Welcome to Lecture 10, 3.1, Measures of Central Tendency. So the first objective is determine the arithmetic mean of a variable from raw data. Alright, so a definition. The arithmetic mean of a variable is computed by adding, let me write that in, gotta get my pen, by adding all the values of the variable in the dataset and dividing by the number of observations. The population arithmetic mean, which we use this character pronounced mu, is computed using all the individuals in a population. The population mean is a parameter. Keep that in mind. The arithmetic sample, or the sample arithmetic mean, denoted x bar, pronounced x bar, is computed using sample data. The sample mean is a statistic. Okay? So the difference here, population mean is called a parameter, and the sample mean is called a statistic. So the formula for sample and population mean, it's not too different, but it varies slightly. So if your data observations are n, capital N, notice, observations of a variable from a population, then the population mean is given by adding up all the values and dividing by capital N. Very similarly, if these are your data values and there are n observations, then the sample mean is you add them up and divide by n. So pretty much there is no difference at this moment. There will come a time when there is a difference, when you're computing between population and sample. So keep that in mind. For example, you are given the following data to the right of student scores on an exam. Compute the population mean. Alright, so we are given a population, and computing the mean, what we're told is population would be mu, so mu is going to equal the sum of all the, so real quick, hopefully you've seen it before, if not, that's okay. This weird looking symbol there is called the sum. So it's the sum of all the values. So right here we have all of our values. Let's go ahead and write those down and then add them up. You can pause the video and try to work on this by yourself. Ooh, kind of lifting off there, okay. 83 plus 74 plus 91. And then what are we supposed to divide by? Well, the number of observations that we see. So how many are there? 1, 2, 3, 4, 5, 6, 7. Adding all of those up, I got that mu equals 562 divided by 7, which is approximately, and I did not give an actual number to round up to, or an actual decimal place to round up to. So what we're going to do is round to the nearest tenth. Normally, they will tell you what to do for this. If they do not tell you, or if instructions are not given on how to round, you can go ahead and round to the nearest tenth. But more likely than not, on homework problems, they will tell you what to round to. So right there is the mean, population mean. Now we're going to find a simple random sample of size n equals 4 students. Okay, so real quick though, before we go on, is this a statistic or a parameter? Well, what did it come from? It came from the population mean, which means it's a parameter. Alright, so now what we're doing is we're going to take a simple random sample of size n equals 4 students. Okay, so you can go ahead and there is a way to calculate this using, let's see, either your TI-84 calculator or StatCrunch on Pearson. If you want to know how to use your calculator, you can go ahead and look on page 112. Okay, so pulling out a simple random sample with our calculators, I got Kevin, Kayla, the other Kevin, and Ava. Okay, semi-simple random sample. I'll write this down. Kevin, I'll call him Kevin 1, 77. Ava, 62. Kayla, 83. And Kevin 2, 74. Alright. Now we're going to compute the sample mean for the sample found in part B. So the sample mean, the only real difference here between the way we compute these is basically the number of ones we have. So the sample mean, x bar, is going to equal the sum of all our xi values divided by n. And let's see, all of our values, so 77 plus 62 plus 83 plus 74 divided by n, which is 4. And what do we get? All right, 296 divided by 4. 74. Ooh, is that exact? 296 divided by 4 is indeed 74. No rounding there. Awesome. So our mean is 4. Now here's the question. Is this a parameter or a statistic? Oops, spelled that one wrong. This came from a sample, which means it's a statistic. All right, let's take a look at the next objective. Is determine the mean of the variable for raw data. Okay, the median of a variable is the value that lies in the middle of the data when arranged in ascending order. We use M to represent the median, capital M, please note. All right, so we have two options. We can either have an even amount of data or an odd amount of data, and that does change the way we calculate our median. So, if the number of observations is odd, then the median is the data value exactly in the middle of the data set. That is, the median is the observation that lies in the n plus 1th divided by 2 position. If the number of observations is even, then the median is the mean of the two middle observations in the data set. That is, the median is the mean of the observations that lie in the n divided by 2 position and the n plus 1 position. All right, let's take a look. So we're given some data to the right that represents the length in seconds of a simple random sample of songs released in the 1970s. Find the median length of the songs. All right, so we have a bunch of songs here. You may or may not recognize some of the titles. I definitely recognize Staying Alive and Heart of Glass. So let's see. Well, the first thing we need to do is arrange these in ascending order, which means the smallest one first. So who's the smallest? Southern Nights. So 179. Then what's next? 201 looks like the next one. After that we have 206. Then 208. Then 217. 222. And 257. All right, we've arranged it in ascending order. So now what we're going to do is, let's see, do we have an odd or an even amount of observations? What is n? N is, let's see, 1, 2, 3, 4, 5, 6, 7. 7. Which is odd. This means that our median is the observation exactly in the middle of the dataset. So the observation exactly in the middle is going to be right here, 208. Okay. So M equals 208. All right, let's take a look at the next example. Given the data to the right that represents the score each student obtained on an exam, find the median exam score. So what is our plan? Well, as usual, just write out the data in ascending order. So let's first do that. 62 is the smallest. After that, we have 74, 77, 83, 85, and 90. Yeah, my handwriting's getting messy. Okay, then we have to see how many observations we have. N observations. Let's see. 1, 2, 3, 4, 5, 6. 6. Which is even. Okay, so that means we can't just pick the one in the middle. This means we need to have the mean of the two middle values. And the two middle values are 77 and 83. We need to find the mean of these two. So our median is going to equal our two middlest values divided by 2, which is going to be, let's see, 77 plus 83, 160. Dividing that by 2 should be 80. So our median is 80. Okay, so remember 2 different ways on if you have an odd amount of observations or an even amount of observations. Okay, so read page 144 of the book to learn how to find mean and median with technology. All right. Let's see. Objective 3. Explain what it means for a statistic to be resistant. All right, here's a question. Which measure of central tendency is better to use in statistics, the mean or the median? And the answer is actually, it depends. Which is why a lot of the times when you have any sort of statistical research you're reading or you see any statistics anywhere, be sure to take a moment and see what exactly their data is and how they're using it. Okay, always keep that in mind. Example 4. Nainoa wants to know how much time he typically spends on his cell phone. He goes to his phone's website and records the call length for a random sample of 12 calls, shown in the table below. Right here. Find the mean and the median length of a cell phone call. Alright, so let's go ahead and find the mean. First off, should I use mu to represent the mean or x bar? Well, since we're looking at a sample, we're going to be using x bar. And x bar, what you do, you're going to go ahead and add up all the values and divide by the number we see. And we know there are 12 calls. We have 1, 7, 4, 1 in the first column, or the first row. Then 2, 4, 3, 48. Wow, that's a long call. 3, 5, 3, 6. That's actually not a long call. I think I talked to my sister longer than that. All right. Okay. Go ahead. Try calculate that out by yourself and check back with me. And we get 87 divided by 12, which is 7.25. So, as I said before, we can go ahead and round out to the 10th if not otherwise mentioned. Actually, you know what? Let's just go with 2.5, because it already ends there. I'll be sure to include rounding instructions on your exam. So that is the mean. And is that a statistic? Or parameter? The word statistic just kills me to spell. Okay. This came from a sample, which means it is a statistic. A way to remember that actually I think is helpful. S for sample, P for population. Okay, let's see. Next thing, we did the mean. Check. Now we have to do the median. How do we find the median? Well, the median, you got to go ahead and list everything out. Let's see, I'll do the median in a different color. I'll go ahead and work with blue. Let's list this out in ascending power. 1, 1, 2, 3, 3, 3, 4, 4, 5, 6, 7, 48. Well, we know that our observations is 12, which means we have an even number. So we actually have to find the two innermost values and then take the mean of that. So the middlemost values are going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5 on each side. So the 3 and the 4, and then divide by 2. M for mean, 3 plus 4 divided by 2, that's going to equal 7 divided by 2, which is going to be 3.5. Okay, so one thing you might notice is I counted duplicates of the same value, and you're going to do that when you're using your data. Okay, make sure to include the duplicates. So M equals 3.5. We'll go ahead and box that. Now, we're going to draw a dot plot of the sample call lengths. Let's take a look. Listing this out. Okay, let's see. The highest value we see is 48. So let's go ahead and graph this in sevens. So 0, 7, 14, 21, 28, 35, 42, and 49. And then let's go ahead and plot these values. So 1 appears twice, which is about here. 2 appears once, about there. This is just a rough graph. 3 appears 3 times. 4 appears twice. 5 appears once. 6 appears once. 7 appears once. And then 48. Whoa, all the way over here appears once. That is that's sort of an outlier hanging out over there by itself. And we used this in our data to calculate, even though it's super far away from everyone else. So, which measure of central tendency better describes the length of Nainoa's typical phone call? Take a look at our two measures of central tendency. We have one, which is 7.25, and another, which is 3.5. These are both measures of the central tendency of our data. Which one actually seems to match our data? Let me go ahead and graph them. I'll do statistic 7.25. Let's see, that's a little past 7. And the other one, which is about 3.5. So about there. Oops. Which one of these values, so the 3.5 was my median, and the 7.25 was my mean. Which one do you think is a better way of telling us what the median, or the middle, or the central value is for my data? Well, the one that looks more like it's in the center of the data, actually is the median. This one looks like it's more in the center of the data. So, in this case, it actually looks like the median is the better one that describes the length of Nainoa's typical phone call. So the median is the better measure of central tendency. Okay, but notice this is not always the case. Sometimes the mean might be the better measuring of central tendency. So the reason for this one, why the mean wasn't the better one, is because we had this really large outlier over there. And that sadly was counted into our mean. Okay, so what effect can an extreme observation have on the mean but not on the median? Well, basically, the median is based off of the middle value, which does not change. Or is not affected, or is not by the largest observation. The mean is affected by the larger observation, or the largest observation. Okay, so that's one thing to definitely keep in mind. How you compute both of them can be skewed depending on your data set. All right, let's take a look at the next definition. A numerical summary of data is said to be resistant if extreme values, very large or small, relative to the data, do not affect its value substantially. So note, when data are skewed, there are extreme values in the tail, like we saw up here. This is an extreme value in the tail, which skewed our data. And that tends to pull the mean in the direction of the tail, which makes sense here because the mean we had was 7, and it ended up getting pulled a little closer to the tail value here, whereas the median stayed sort of in the center or the central area of our values. And remember, we're looking for the central data. Okay, so our mean ended up getting pulled towards this outlier. For example, in skewed right distributions, there are large observations in the right tail. These observations increase the value of the mean, but have little effect on the median. Similarly, if the distribution is skewed left, the mean tends to be smaller than the median. In symmetric distributions, the mean and the median are close in value. Okay, so fill out the chart below, then sketch examples of the three distributions with their mean and median. Okay, so for skewed, if we have a distribution that is skewed left, what do we know? The mean is substantially smaller than the median. Let's see, in our example up here, is this a skewed left example or a skewed right? Well, when we're talking about skewed left, it's saying the mean is smaller than the median. But in our case, the mean was larger than the median. So this one is not skewed left. This is skewed right, because we've been skewed by a value to the right. Okay. So for skewed right, the mean is substantially larger than the median. And this is the example we saw in our problem above here. This was a skewed right example. Now for symmetric, the mean is roughly equal to the median. Okay, so let's take a mini look at some examples of the graphs. So let's see. 3 sort of graphing areas. Let me take this one back a little bit there. Just a very quick graph on these. And let's see. We can get some. Let's do blue. Alright, so I'm going to draw some images, take a moment to decide which one you think I'm trying to represent, which distribution. Let me redraw that one. Okay. We have a median. Then we have a mean. Then here we have a mean roughly equal to the median. And then here we have the median and the mean. Alright, which one is which? These are all different distributions. Well, the one right here, this is skewed left because we have items on the left pulling our mean out in this direction. So this one is skewed left, where the mean is left. The mean is less than the median. The middle one here, that is symmetric. And in this case, the mean is equal to the median. Or the median is equal to the mean. And lastly, we have items skewed here, which is pulling my mean out to that direction, to the right. So this one is skewed right. Or another way of writing it is my mean is larger than my median. Objective 4. Determine the mode of a variable from raw data. So by definition, the mode of a variable is the most frequent observation of the variable that occurs in the data set. So note, because when computing the mode, you tally the number of observations that occur, a set of data can have one mode, two modes, more than one mode. If no observation occurs more than once, take that out, what we say is that the data have no mode. Okay, so it's possible to have no mode. However, it's not possible to have no median or no mean. Okay, but with no mode, it is possible to have no mode. All right, let's take a look at the examples. The following data represent the number of O-ring failures on the shuttle Columbia for its 17 flights prior to its fatal flight. Find the mode number of O-ring failures. All right, so how do we find the mode? Well, just count the amount of times you see something, and whichever observation you see the most, that's your mode. So what different observations we have? We have 0, 1, 2, and 3. And how many times do we see each of these observations? So I'll call this one the observation, and this will be the number of times we see it. Just a quick little graph here. Okay. How many times do we see 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. How many times do we see 1? 1, 2, 3, 4. How many times do we see 2? Just once. And 3, we see it once. Well, the mode is the one that occurs the most, and which one occurs the most? Is 0. So our mode is 0. And we don't have any symbol at this time to represent the mode. Oops, there's supposed to be an E on the end. Alright, so find the mode of the exam score data listed in the table provided. Alright, so once again, what we're going to do is write down each data set and see how many times it occurs. So we have our observations, and we have the number of times they occur. Let's see, we have 85. Actually, let me write this out from smallest to greatest. 62, 74, 77, 83, 85, 90, and 91. And 62 appears only once. 74 appears once. 77 appears once. 83 also appears once. 85 appears once, 90 appears once, and darn it, 91 appears once. They all appear the same exact amount of times, so there is no mode. Sad face. Okay. Note, if a data set have two modes, we can say that the data are bimodal. This is actually supposed to be one word or hyphenated. If a dataset has three or more dataset values that occur within the highest or with the highest frequency, the dataset is multimodal. Let's take a look at this example. Find the mode of cell phone call links in the table provided. All right, so we have our table. Once again, let's go ahead and do observations and the number of times we see them. I don't like that line. Aha, okay. And we have 1 is one of the observations. 2, 3. Ooh, let me back that up. 1, 2, 3, 4, 5, 6, and 7. Okay, so we have these different values here. How many times do we see them all? We see 1 2 times. And then we see 2 just once. And we see 3, 1, 2, 3 times. You can go ahead and pause this video and figure this out on your own if you'd like. Or you can follow along with me. We see 4 3 times. We see 5 once. And then we see 6 once. And we see 7. How many times do we see 7? Also just once. Okay, so which one occurs the most? Oh, well, what do you know? These guys occur the same number of times. They both occur 3 times. So 3 and 4 both occur 3 times, which means that 3 and 4 are my modes. So my data is bimodal. The modes are 3 and 4. So for an example of what this might look like for a graph, is we might actually end up having a curve that looks somewhat like this, where we have the two modes, mode 1 and mode 2. That's exactly what it might look like. Alright, that is it for 3.1. Please email me if you have any questions or need help with the homework.